good morning, or good afternoon, or maybe it's good evening, whatever. What I want to talk to you today about is comparing intramolecular forces. Okay, these are forces that hold molecules, compounds together. The word that we use for that is bonds. And there's three words that you need to have a handle on here: ionic, covalent, and metallic. Ionic, if you remember, we have valence electrons that are being transferred. Typically a metal gives electrons to a nonmetal, creating a positive ion and a negative ion. And their ionic bond is this attraction here. Covalent, you have two atoms that really don't want to give up electrons, and so they share them. And this usually happens with nonmetal atoms, but we'll get to that. And then finally, metallic. Here you have the nuclei of metal atoms that are attracted to this. It's a sea of electrons. These are delocalized, meaning they're not attached to any atom, so they're free to move throughout the metal, and that's kind of what holds the metal together, and it gives the metals some pretty unique properties. Okay? Now, you should have a template like this. And what I'm going to do is I'm going to walk through this template, and as I go through it, you can fill your own template out. Hopefully that's in your notebook. So, metallic bonding occurs when metals bond to each other. Pretty simple. Ionic bonding occurs when cations are attracted and bond with anions. And the word that you're going to hear me refer to sometimes is called lattice. We talk about the lattice of an ionic compound. We'll deal with that a little bit later. And covalent bonding is when two atoms share electron pairs. Okay? And it occurs between, for a metallic bond, it occurs between metal atoms. Ionic bonding it occurs between something that's a metal and something that's a nonmetal. Remember, metals form cations, nonmetals form anions. And the operating thing here is we have a connection here based with ions. Covalent bonding, we're talking about nonmetal atoms that are creating that. And the bond characteristics, we talked about delocalized valence electrons are shared. That's probably the unique characteristic for a metal bond. For an ionic bond, the ions are held together by an electrostatic attraction. Positive is attracted to negative. And then finally, here we're talking about the sharing of electrons, valence electrons. And the electrons that we're talking about here are always valence electrons. Examples. Well, for a metal, I could have an alkali, an alkaline earth, or transition. Anything that's a metal on the periodic table can exist as a metallic bond. So iron, magnesium, sodium. I could pick any element I want that, as long as it was on the left-hand side of that stairway on the periodic table. For an ionic bond, any type 1 metal and a nonmetal. So sodium chloride, calcium bromide, and really some transition metals can probably also fit within this. And for covalent bondings, what we're talking about is between non-metal atoms. So carbon dioxide, carbon tetrachloride, and also polyatomic ions exhibit covalent bonding. And if you look at that, sulfur and oxygen, phosphorus and oxygen, so it's phosphate, sulfate, those are examples of covalent bonding. And then down here I have just some properties of these bonds, and we're going to be working with these properties in the lab very shortly, and so we could talk about that. Let me put that on. When we talk about melting boiling point, metals have very high melting points, as do ionic compounds. But most covalent compounds have low melting points. Solubility in water, guess what? Metals are insoluble. Insoluble means they don't dissolve in water. Ionic compounds are soluble, and covalent compounds, I'm going to say it depends. We're going to need to take a look at the intermolecular forces, not intra, but intermolecular forces here, and we'll talk a little bit more about that later. Conductivity, I would say excellent. Metals are very good conductors. Ionic compounds are poor, and again, we are in a solid phase here. And this is usually poor also. But if we put it in a liquid state, if we melt it, guess what? This is still very good. Ionic compounds, if you can melt them, they are also good conductors, but not so much for covalent. And finally, conductivity in aqueous solution. This is something that's been dissolved in water, because metals don't dissolve in water. We don't worry about that. Ionic compounds are usually very good conductors if you dissolve them in water, and guess what? Not so much for covalent. Okay? So just to summarize here, when we talk about ionic, we got ionic right here, covalent right here, think of a continuum, and a continuum is all based on electronegativity difference. If the electronegativity difference between the two parts of the compound is very large, we call it ionic bond. If it's very small, we call it a covalent bond. And again, electronegativity is the attraction of the nucleus for shared electrons. So if it's a large electronegativity difference, that means one party really wants it and one party really doesn't want it. Here, both parties really want it, and so they have to share. And then this part right here, this is what we call in between. Okay? And we'll talk about this whole idea of polar and nonpolar later. Thank you.